Okay, this is chemistry part 2. We ended the first part talking about why atoms interact the way that they do, and that is to fill their valence shell. Except for the first shell that fills with 2 electrons, all of the others fill with 8 electrons. So we're going to be taking a look at chemical bonds. You don't have to jot these down right now. We'll take a look at each one individually. Or actually, you know what? It might not be a bad idea to write them down. And then you can also make a notation that this list is from, and I can hold, strongest to weakest. So covalent is the strongest, ionic is the next, and hydrogen is the weakest out of these 3. This isn't a complete list of all the bonds that can form. This is just a list that we are going to be covering. I'm going to be going over examples for these, and you are responsible for the examples that I cover as well. I expect you to know those examples backwards and forwards. All right. So again, keep in mind, atoms want to fill their valence shell. All right. So now we're going to go into covalent bonding. Covalent bonds are formed by the sharing of 2 or more electrons. So they're going to interact to fill their valence shell, but they are going to do so so that they can fill their valence shell. So we can take a look at carbon as an example. So we see, and you're just going to have to go back to your previous notes. I don't have the space to cover this. Carbon has 4 valence electrons. The hell with it, I will. Carbon has an atomic number of 6, which is a number of protons. We can assume that the atom is neutral, so the protons will equal the electrons. So first shell fills with 2. Second shell fills with 4, because that's what's left. So since we're only concerned with the valence shells, we plug them in. And now we know that carbon needs 4 more electrons to fill this valence shell. If we take a look at hydrogen, hydrogen has 1 electron. So it needs 1 more to fill its valence shell. So what's going to happen is a hydrogen will come along here. Hydrogen will come along here. Another hydrogen here. And a hydrogen here. So that if we take a look at just this bond right here is going to be formed by carbon sharing its 1 electron, hydrogen sharing its 1 electron. And in this case, hydrogen is now happy because hydrogen filled its valence shell. Carbon isn't happy yet, but it has to do that same exact thing 3 other times. So now carbon will have, in essence, 1, 2, 3, 4, 5, 6, 7, 8 valence electrons. So that's why we have methane, CH4. We can also take a look at oxygen. Oxygen, let me do it over here. Oxygen has the atomic number 8. First shell fills with 2 electrons. Valence shell then is 6. So oxygen has 6 valence electrons. 1, 2, 3, 4. Let me do 5 and 6 right here. So it needs 2 more. So if we do the same thing that we did with the carbon, hydrogen will come along here. Hydrogen will come along here. And that's why we have H2O. Okay, so oxygen has 8 valence electrons and each hydrogen has 2. So all of the atoms are happy. Their valence shells are filled. Don't worry about why the hydrogen is second here versus here. We're not too concerned about that. Now, that alone doesn't explain everything that's going on, because when we say that they're sharing electrons, they're not really sharing. There's a tug of war going on between them. And just like with a tug of war, if you want to know who's going to win, you want to know who is stronger. So what we do is we measure an atom's strength, and this is also later on. Measuring that strength is called electronegativity. It measures an electron's affinity or drawing power for electrons. Okay, so that's going to tell us how strong these atoms are, and if one is stronger, it will win that tug of war. So I'm going to move on to the next slide. Just keep in mind that electronegativity. So here's the example of methane CH4 that I just covered. And now we're going to get into the polar versus non-polar. So carbon to hydrogen, there would be three others. I'm just trying to save some space. These guys have an equal strength. So that tug of war is a push. So because of that, there is equal sharing. Oxygen to hydrogen. Oxygen has an incredibly high electronegativity. In terms of electronegativity, you have to know that oxygen and nitrogen are the two atoms that have a tremendous amount of electronegativity. They're like atoms on steroids. So what's going to happen? Keep in mind this dash is actually two electrons, one from hydrogen, one from oxygen. This electron is going to start spending more time by this oxygen because of its electronegativity. So when that happens, hydrogen is going to start to be positively charged and oxygen is going to start to be negatively charged. So that is unequal sharing. So when we see that, when electrons are shared equally, that is going to be non-polar. And unequal sharing of electrons means that that bond is going to be polar. There is still an equal number of electrons and protons in both of these cases. It is just the distribution that is different. So here's my CH4. Anywhere on this molecule, it is going to be neutral because there is an even distribution. Whereas if we take a look at a water molecule, this oxygen is going to be negatively charged and these hydrogens are going to be positively charged because oxygen is pulling those electrons towards it. Okay, so oxygen has polar covalent bonds. Water has polar covalent bonds, and methane has non-polar covalent bonds. Okay, ionic bonds. This is from the transfer of electrons. So that's from the transfer of electrons. So the only example that we are going to talk about is sodium. Okay. Excuse me. The next slide has an image of this. I would rather see you see how it is constructed first. So if we take a look at sodium, sodium has an atomic number of 11. So that means we have 2 electrons, 8 electrons, and then 1 electron. So sodium needs 7 more. Chlorine, atomic number 17, 2 electrons, 8 electrons, 7 electrons. Chlorine needs 1 more. Now keep in mind, these atoms want their valence shell filled. It's very unlikely that sodium is going to find 7 electrons. Okay? And I just want to make sure this is a 1, not a 7. So it only has this 1 electron in its valence shell. And again, this valence shell is whatever the outermost is, so it is dynamic. It can change. So what if sodium got rid of its electron, transferred it to chlorine? Chlorine would gladly accept it, and when it gets rid of this electron, its valence shell now is this second shell. So now, with sodium, since it lost an electron, is going to be positively charged. Chlorine is going to be negatively charged because it gains an electron, and it's that opposites attract. That's where that ionic bond is going to be formed from. And we can see that here. They're just showing this lone valence electron that is going to be transferred to chlorine because chlorine only needs 1 more. And then when it loses this valence shell, so what we see over here, so now this second shell is the valence shell and that's filled and it is positively charged. Chlorine's valence shell is filled. That's happy. It has a negative charge. Opposites attract. So there's going to be a bond formed between them. Okay. Hydrogen bonds. I'm going to just, I think that's it. Yeah. I'm going to leave this. You can pause it right now to write this stuff down. I'm going to talk about it. Actually, I'll even try and do it right here. There's enough space. Hydrogen bonding, students don't like. No, that's not going to work. Let me do it down here. I have no idea why the pen keeps doing that. So hopefully you guys are all right with why oxygen is negative and hydrogen is positive, right? Because of that electronegativity. So if hydrogen is bound to either oxygen or nitrogen, because again, these two are the ones that are electronegative, this is the situation that we're going to see. But in a glass of water, there are millions of water molecules. So this is negative, this is positive. A hydrogen bond is this weak bond because this is positive, this is negative. Okay? So in order to have one end be positive and one end be negative, we need to have oxygen or nitrogen covalently bound to hydrogen first. Then it can win that tug of war, and then we see a hydrogen bond will be between molecules. And hopefully that made sense, and hopefully you can see that here. Oxygen is negative, hydrogen is positive, so there's our hydrogen bond. Okay? So they are incredibly, incredibly weak. They form and break 1 million times a second because the kinetic energy, this water molecule is moving, and let's say it's moving this way. The minute it gets so far, then this hydrogen bond will break. It'll get close to another one, and then another hydrogen bond will temporarily form. Okay? And it's because of those hydrogen bonds, it gives water some unique properties, and I'm just going to kind of list them. And then we're done. So we only have a couple more properties to cover. High heat capacity is a property of water. It can absorb and release large amounts of heat before changing temperature. Not too concerned about this one, but coastal areas will be cooler because it has a large body of water right next to it. What is more pertinent to the human anatomy and physiology is high heat of vaporization. Changing from a liquid to a gas requires a large amount of heat. And the reason for that is if here's this water droplet, we have a water molecule right here, and then we're going to have another one right here. This water molecule right here is being pulled towards the center from these hydrogen bonds. So this guy, this water molecule that's at the surface needs more energy to stay where it is. So because of that, when we go from a liquid to a gas, it's always going to be the surface molecule that goes first. And because this has more energy, because of this hydrogen bond, it's going to take more energy for this water molecule right here to leave this liquid and enter a gas form. So what is the importance of that in human anatomy and physiology? When we get hot, we sweat. It's not the production of sweat that cools us. It's the evaporation of sweat. By having this liquid on our skin, as this evaporation takes place, so much energy is required to have that happen that our body temperature will go down as a result. Polar solvent properties. You remember what a solvent is. It is the dissolving medium. And this is that like dissolves like. You already know oil and water don't mix. Why? And that's because oil is nonpolar, water is polar. So if something is going to dissolve in water, it has to be polar. And here's an example. The reason why salt dissolves is because salt is polar. It has a charge. Don't get confused between a polar bond versus something that is polar. So this is polar because it has a charge, even though it was an ionic bond. That ionic bond will be disrupted, and we'll see what are called hydration shells. So this is positively charged. It's going to be surrounded by the negative oxygens. Chlorine, as an anion, it is negatively charged. It will be surrounded by the hydrogens. So like dissolves like. So what that means is if we have fat is nonpolar. And if we need to transport that through our body, the rest of our body is polar, we have an issue because the fat won't dissolve in the water. So you have to understand this polar and nonpolar interactions. Like dissolves like. You add oil to water, that oil will not interact with the water because the oil is nonpolar. All right. Okay. More properties. Reactivity, an important part of hydrolysis and dehydration synthesis reactions. Memorize this. In the upcoming sections, we're going to be talking about this. No point in me going over it right now. When we get to macromolecules, we'll talk about hydrolysis and dehydration synthesis. Okay. You do have to know this. It's just, I will cover what this and this is in greater detail later. And this you don't even have to worry about. It's your fun fact of the day. Like no other substance, it exists naturally in all three states of matter. The only other thing that I want to say, the only other property is that the solid is less dense than the liquid for water, which means ice floats. And the reason why ice floats, if you take a glass bottle, fill it up with water, and then put it in the freezer, that glass is going to break because water expands. The reason why it expands is because once we reduce that kinetic energy, that energy of motion that these water molecules have, we're allowing every single hydrogen bond to form, and it creates this crystalline lattice structure. So we can see that here. In the liquid form, right, these hydrogen bonds are forming and breaking because the kinetic energy, these water molecules are moving all over the place. Once we freeze it, we stop them from moving. I mean, technically they're still moving, but for our purposes, we can say that they stop moving. So we allow each and every single hydrogen bond to form. And because of that, that causes that expansion. And because of that expansion, right, that's why it's less dense and ice floats. I know this was a lot for these first two sections. You're probably going to have to listen to these multiple times. I'm just trying to make this so you don't have 20 different recordings to listen to. All right. So as always, let me know if you have any questions. And part 3, we will continue our discussion.